All right, and hello everybody. Welcome back. I'm creating a series of videos on the topic of how did I measure or obtain or calculate the weight of the robot. This is part 3. I do have a YouTube channel and I invite you to subscribe. I think you will like it. I do have a website. This is the area where these hydraulic walking weight of the robot videos are located. I do like to remember to remind everyone any physically real object has the potential to hurt somebody. If you are managing a physically real object, my advice is to manage it in a manner that is legally allowed and reasonable and safe. And if you cannot manage it in that way, then my advice is do not create it as a physically real device. And let's see, this is on my desktop. What do we have today? Microsoft changes this. Casa del Prado in California. It would be quite a house to live in, wouldn't it? And we're showing this in Keyshot. So before we continue on the weight of the robot, I wanted to touch on something that's important. I took this metal rod, which is a vertical rod, and duplicated it so we can move it around. And I wanted to show that this, I think, I'm just using my eyes, is about where the center of mass of the robot is, particularly from left to right, and it's probably going to be about right there. And that reason why that center of mass is there is because the robot has its weight on its 2 feet. And its arm is in the air, and its arm is displaced to the right of the center of mass because it's the right arm of the robot. And so our next maneuver is move selection. Okay, so our next maneuver is to go over here. And the question becomes, why did we do that? And the answer is, if the robot puts its hand up here on this bar and it flexes its hips and knees a little bit, but it flexes them enough that the feet of the robot are off the ground, then right now the hand of the robot is to the right of the center of mass, but under the influence of gravity, the robot is going to rotate so that about half of the weight of the robot is to the right of the center of mass, and the other half of the robot is to the left because it's going to be balanced. And that is why when you look at these drawings, the robot is tilted like this, because I think you might be saying, why is the robot tilting himself like that, or herself? But that's what's going on. Now let's go look at some other drawings. And I got this vertical rod here again, and this is the robot where he has lifted himself up to 16 inches, and there's his hand. And I don't know, he might be, actually would be more tilted a little bit more this way, but the reason for this is because that is the suspension point of the robot. And now we'll move over to the situation here where the robot has let go of the bar. And the bar, this is not a bar that you would encounter out in the woods. All right, so there is where his hand is when he let go. And I think that this is closer to the angulation of what the robot would be like than the one over here. This one's not quite right, but that seems like about as much of the robot is to the left of the bar as it is. Once the robot lets go of the bar, on the conservation of angular momentum topic, the robot can move itself in an angular manner if its feet are on the ground, because the feet act as an anchor point, or if the hand is holding the bar. But if the feet are not on the ground and the hand is not holding the bar, the robot is free in the air, and it can't create angular momentum for itself. Whatever it moves that creates angular momentum in one direction, it has to move something else that creates angular momentum in the other direction. That's just one of those rules. And I wanted to discuss that because it's very counterintuitive. And so you can see where the hand is here. The robot just let it go. And I have on this bar, I have these 4 marks. And the reason for that is to make sure that I had the hand in the same place every time. And so now the robot has let go and the robot has fallen. You can see that the hand has moved down a little bit. And the robot has swung this left leg over. And I wanted to discuss that because you might say, oh, hang on a second now, that robot can't do that. And that's what I wanted to address. I kind of went over it really quickly, and I wanted to spend a little more time on it. The summary position is, okay, so that's to show you that hand. So we'll get this out of the way where it's not bothering anybody. And say, okay. So this leg, if you look at this leg and draw a line through it, that line points to about right there. So that is the angle of the leg with respect to the body of the robot. And you can see that the entire leg rotates around this pivot point. That is this piston is the piston, or this hydraulic cylinder is the hydraulic cylinder that controls abduction, adduction of the leg. And you can see where this hydraulic cylinder is. It's about that distance right there. And if we want this leg to swing this way, then this is going to need to retract, and that's the next thing I want to show you. And we're coming up on this leg, and you can see now, if you take the angulation of the leg, it used to be over here, but now it's pointing up to there. It's kind of pointed at the shoulder. And I'm trying to get the contact point, the impact point, to be under the center of mass of the robot. Really, we want the left leg to be to the left of the center of mass and the right leg to be to the right of the center of mass. And you can see that what happened to do that is this hydraulic cylinder this hydraulic cylinder is substantially more retracted than it was. And when it retracted like that, it rotated the leg out. And the question becomes, so can the robot do that? And the answer is, we set this to move at 15 centimeters per second because we're duplicating human muscles. And you can take this distance that this piston head moved, and you can take this amount of distance that the robot fell, and you can do a calculation. And the calculation is the robot went down 4.3 inches. Acceleration of gravity is 32 feet per second. Per second will take 0.15 seconds. Left leg abduction piston retracted from 1.4 to 1.0. The distance is 1.4 minus 1.0, 0.38 inches. 38 inches is 0.9674 centimeters. So the travel of the rod was 0.9674 centimeters divided by 0.151 seconds for a travel rate of 6.4 centimeters per second. And what it says is, yes, the robot can do that. And this is something that I think is fundamental to understanding hydraulic cylinders in these robots, because they give the robots the ability to do all this stuff that the electric motor gearhead robots can't do. So if the electric motor gearhead robot let go of the rod and started falling, it would land like this because it can't do that. And here I think I have it falling a little bit more, and I have it swinging its legs over. And I'm just trying to guess, as a human being, how would this work exactly? Just put it where you would put it. Do what you would do. And human beings, compared to robots, human beings are fantastically good, just godlike in their ability to move around and balance and land and walk compared to robots. And so if we're going to, we should mimic a human being. If we truly mimic a human being, then we don't have to ask ourselves, well, what are we going to do? Because all you have to say is, well, what would you do? And tell the robot, do that, which it can do if you use hydraulic cylinders. And so now we're on the third section of this this drawing. And we'll go to here. So he has, or he or she, you know, I'm a he, so my robot is a he, but I guess he could be a she. It doesn't much matter. But he got his left leg very close to touching the ground. And what will happen is the central processing system will be monitoring pressure, touch, sensation from these toes. And when it picks up that these toes are on the floor, it will tell the robot to start flexing this knee, because these toes aren't on the floor yet. These toes are on the floor, these aren't. So it'll say lift this up, because what we want to do is land on both feet. Can this be done? Absolutely, it can be done with a hydraulic cylinder robot. It cannot be done with the electric motor gearhead because they're not fast enough. And the pelvis is sort of lined up right beside the left leg, and we want the pelvis to move over a little bit because we're getting ready to distribute the weight between the two toes, 2 feet. And so now we have the robot standing kind of square with the pelvis over the middle. The center of the pelvis is located halfway between the right and left feet, and the thing that's left to do is to straighten up the thorax. And this is how the robot lands on the floor. And if you use 2205 alloy stainless steel, and if you use hydraulic cylinders, these feet and legs, they don't care. It dropped 16 inches and landed on the floor, and not anything at all will happen. And I can show that by math, but I need to have the weight of the robot in order to show that. And that's the next thing I wanted to show you. All right, this is a little interesting. She stood up, jumped up in the air, came down, landed on her 2 feet, and in her hand she held out a little note, and the note says, "You are done. Time." All right, well, we'll stop this one and start another one.